Today we're going to finish up the packet, and we are actually going back over some stuff that we've already talked about. So really it's not too bad. The image that I have here, I believe that we're looking at a copper wire here, and I know you can't see it in your notes because it's in black and white, but you might be able to see it here. I wish they would have used a different background other than a blue background here. And I'm not sure what they use silver nitrate. So they use silver nitrate, which is a solution here, which is clear or transparent with no color. Place the copper wire in there, they kind of coiled it up. And then we notice that there's something adhering to the copper wire. And what you can't see, or what you really can't see, is that this solution has gone from a clear color to a blue color because they have a blue background, which is awesome. What that's showing is that the copper ions are actually leaving from a solid and going into the aqueous state. And just like when we did our hydrate lab, everybody's turned the hydrate lab in already, that was copper sulfate. And when copper ions go into solution that have a +2 charge, they'll generate this bluish tint. And what's happening is the copper metal atoms are actually going into solution, and the silver ions are coming out of solution, forming pure silver along this copper wire. So it's a single replacement reaction, things that we've already done before. However, when you look at this, we've got a solid and we're placing it in a liquid. Typically what I'll do on a problem like this is I will give you the volume and the molarity, just like what we talked about earlier in the mole section, and there's the examples. If I'm giving you the volume and the molarity, we always start with the volume. Okay? If it's in milliliters, convert it to liters, and then if you have that liter of volume, then we can cancel out the liters in molarity, which is moles per liter. So that would be considered step 2. So if you're given a molarity, then I'm probably giving you a volume with that. Now, if I ask you to find the molarity, which I hope one of these questions will do, and we'll do it once we turn the lights back on, then we have to do something a little extra. So hopefully we'll be able to do that. Part of the homework is the 4s. We'll do that after we do the examples. Adjusting to reality. And actually this is part of the explanation as to when we did our hydrate lab, why we didn't get a perfect whole number. And here's some of the things that may happen. The reality, some reactions are not very reactive. Okay, we have to do a lot of things to get them to be reactive. The conditions that are required might be that we have to heat it up a little more to get it to react. We might have to dissolve it in a solution a little more to get it to react. We have to get it, crush it up a little more so there's more surface area. There's a lot of things that have to take place. Like for example, in that hydrate lab, some of you used the larger crystals versus the smaller crystals, and I'd be willing to bet if you were careful, you might have got better results with the smaller crystals, because with the larger crystals, it's hard to get the water out of the middle of the crystal. Okay, but if we would have crushed them up, it would have given us some better results. So, some ideal chemical reactions, when atoms are colliding, we'll talk about this a little bit later on. There's a right way to collide and there's a wrong way to collide. All right. So in some collisions, it might not produce a reactant or a reaction there. Bonds are broken between the atoms or ions. Sometimes the bonds aren't broken. Sometimes they're never even met. Okay. Other atoms can't get to them, so they can't break those bonds. The intermediates, which we'll talk about in AP, aren't formed. And finally, the products that are actually being formed may not have a chance to form because the other reactants that haven't reacted yet can't find each other. Okay, so there's a lot of scenarios that could take place. When we talk about things being in excess, all right, whenever we have a reaction, we don't always have a perfect scenario where we're always going to run out of all the reactants at the same time. Somebody should be in excess, or we should have extra at some point. If something is not in excess, what that means is it is totally consumed in the reaction. And if something is totally consumed, once it's consumed, the reaction stops. And I'll do an example on the board once we get the lights turned on here. And we'll talk about those here in a little bit. So let's look at the examples here. Let me turn the lights on. And the bad news is I'm going to work that homework problem out for you. So the homework is only in example number 7. It says in a single replacement reaction, aluminum metal replaces zinc in a zinc nitrate solution. Here, let's write that first. So we have aluminum metal, which is just Al, replaces zinc in a zinc nitrate solution. I shouldn't have done that. Yeah. Okay. All right, so aluminum's trying to replace the zinc. Now, before we go any further, what's the charge on zinc?
+2.
Good. And nitrate?
-1.
1. So we do need 2 of those. Okay. So if this takes place, and it will because I gave you the problem for this, what are my products going to be? Aluminum replaces zinc. Good, so we'll have aluminum nitrate. We'll write that first. And then the zinc will be standing all by itself. Okay. What's the charge on aluminum? +3. And then nitrate's still going to be -1. So we need 3 of those. Now, don't automatically go, oh, well, there is a 3, so we don't need to write a 3. I'll do that. All right. And so we have that written correctly. So let's continue and read the problem. We haven't bounced it. We're not going to worry about that yet. Calculate the mass in milligrams of zinc produced. So milligrams of zinc produced in this reaction when 200 milliliters, that's right here, 200 milliliters of a 0.44 molar zinc nitrate is reacted with 0.305 grams of aluminum. Okay. All right, so what we have here is we have a lot of information, don't we? Anytime you see an amount or 2 amounts for, or an amount for each reactant, you have what's called a limiting reactant problem. Now, what is a limiting reactant problem? Let me do a little sidebar here for you. Let's say that I want to make some cookies, okay? And this is my diameter for the cookie that I plan on making. And it has a certain thickness as well. And I have enough dough to make 100 cookies at that particular diameter, whatever it is. And then I plan on placing exactly 4 M&Ms on each of these cookies. Okay, so there's 4 M&Ms. I love M&Ms. Okay, so there's 4 M&Ms per cookie.
Maddie said it looks like a button.
It's a cookie. Cookie.
Put in little M's on the circles.
No. Okay. So I go and buy a bag, a big bag of M&Ms, and then I count out, and there's only 375 M&Ms in the bag. Now, this math should be pretty straightforward. Who am I going to run out of first? The dough or the M&Ms to make cookies with 4 M&Ms? Now, and here's what we cannot do. We can't break the M&Ms apart, put parts of an M&M on there. We can't change and make it with 3 M&Ms because that's wrong. Every bite should have an M&M in it. Okay? You want the consistency, right? Okay. So, who are we going to run out of first? The dough or the M&Ms? The M&Ms, okay? And once we run out of M&Ms, we're done making cookies with M&Ms. Okay? So our limiting reactant in this case is our M&Ms. Okay? Same thing here. One of these is going to run out first. If and again, hypothetically speaking, we'll say that the aluminum is my limiting reactant. I don't know if it is or not. We're going to solve for it. But if it is, it's hard to make aluminum nitrate when you don't have any aluminum. Okay? Or if you run out of zinc nitrate, it's hard to make aluminum nitrate, the nitrate component, and zinc if you don't have any. Okay? So that's what limiting reactants are about. How do you determine who the limiting reactant is? How'd you do it there? with the M&Ms and the dough. You did the math in your head. You actually did some stoichiometry in your head. That's how good you guys are. I know, right? So here's what we're going to do. We're going to do what's called, if we have two amounts for the reactants, or if we have an amount for each reactant, it's called a limiting reactant step. I might want to write small because I don't know how much room I gave you.
No, you gave us more than you usually do. So.
All right, good. A limiting reactant step. What we need to do is we need to calculate and see which of these two things is going to run out first. Okay? All right, so, and it doesn't matter if you want to start with the aluminum or start with the zinc. What do you guys want to start with? The aluminum? Or wait a minute, before we do that, let's balance the equation. Is that balanced?
Yeah.
Yeah, so we need 2 there, 3 there, 2 there, and a 3 there. Boy, that would have really messed things up. So in the limiting reactant step, we're still doing the 4 steps of stoichiometry. We just get to do it more. All right, so step 1, write a balanced equation. In the limiting reactant step, which one do you want to start with? The aluminum or the zinc? Good, I like the zinc nitrate as well. So, and the reason why is because we have our volume and our molarity. We've already started with that. So if you know the volume and the molarity, start with your volume. So you have your 200 milliliters. Convert that to liters. And then again, don't forget that the big M represents moles per liter. And that's how we want to show it in our problem. We want to show it as moles per liter. We don't ever write capital M in our factor labeling. Don't do it. No matter how tempted you are, don't do it. Wait, what? Okay. So this all right here is step 2. Okay. In other words, I've changed what's given in the moles. If I were to stop right there, that would give me my moles of, and I'll put it up there, zinc nitrate.
Oh my gosh, this makes sense.
Yeah, what?
Makes sense.
Okay.
There's just like an extra step in there.
Yeah.
And then you go.
And then from here, we do what we've been doing. So we'll put
Stoichiometry step.
moles of zinc nitrate down here. And what are we looking for? We're actually comparing it to our aluminum. So whenever you're doing a limiting reactant step, whatever reactant we started with, we're going to compare it to the other. So we're going to have moles of aluminum,
Isn't there 2 and 3?
2 and 3, from our balanced equation. Now, here's the difference. We want to go back to the unit that this is in, the other thing. So we started with this, so we want to go back to grams. If this were in moles, we go to moles. If it were in volume, then we'd go to volume. And I'll show you how to do that a little bit later on.
We go back to what?
Volume. If, say, these were both volumes and molarities, both of these reactants, and I'll show you here in a second how to do that. So let's put our 1 mole of aluminum down here. You all right?
Yeah.
And then the mass for
I'm dying
aluminum.
back here like Maddie is, but she can't breathe, but she can talk.
Oh. Wait a minute. She can't breathe, but she can talk?
Yeah.
That's unfortunate.
No.
Messed up words after all.
All right, so let's find out what this is. And again, this is step 3, mole ratio. Step 4, change to the desired units. 29 or 26. Mm-hmm.
1.58.
1.58, okay. All right, so here's what this says. And here's how we read it, okay? Okay, and this is what I always tell my AP kids to do as well. Always talk yourself through it. If I use all 200 milliliters of my 0.4 molar solution, I will create, or I will need at least 1.58 grams of aluminum. Again, if I use all 200 milliliters of my 0.44 molar solution of zinc nitrate, I will need at least 1.58 grams. How many grams do I have? Not enough. So, I am not going to be able to use all of this because I'm going to run out of the aluminum well ahead of the chance of this reacting completely. So since I do not have enough aluminum to completely react with all the zinc nitrate, that's my limiting reactant. Okay, not yet. Let me give you the other scenario. Okay, this is, what's the matter? And you only need to do the limiting reactant step one time. However, I do want to show you this other way in case you did start with the 0.35 or 0.305, like Jeremiah wanted earlier. Okay? You only do this one time. Okay? However, if we did start with this, I'll leave that there. Let's say that we did start with the 0.3 of aluminum. What I want to do is I want to get to my volume of zinc nitrate. But before I do that, step one, write a balanced equation. Step two, change what was given into moles. So 1 mole of aluminum, and the molar mass was 26.98. Okay, that's all step two. Use the mole ratio, so moles of aluminum on the bottom, and moles of zinc nitrate on top. And it was a 3 to 2. Now, here's the difference. If you're given a molarity, what are the units for molarity? The units for molarity are moles per liter. And also remember that this represents 0.440 moles for every liter. Okay? 0.440 moles for every liter. If I wanted to get rid of the unit moles, I would have to go moles of zinc nitrate down here. Okay. What number do I put there? 0.44. Because when we look at dimensional analysis, if I have a 0.44 molar solution, that means for every liter of that solution, that's how many moles I have. And just like what we were doing earlier in the year, if it's not the unit you're looking for, move it diagonally. So this right here is this inverted. But the reason why we inverted it is so that we could cancel out our units moles of zinc and get a volume. Then we would go one more step and put our milliliters on top. By doing this, we can find out how many milliliters of this 0.44 will actually react with the 0.35.
So it's like dividing by a fraction, we have to multiply by switching.
But wait, we don't have to do that one too, right?
No. So let me get this first and then I'll talk in more depth here.
It's just multiplied by the receipt.
So 38.5, I think. Okay. Now, here's how you would read this. Now again, it doesn't matter which one you start with. You just have to know how to use it. I think it would be easier if you started with your volume and molarity. That's why I wanted to start with that one first. That's what you guys are accustomed to. However, if we were to react all the aluminum, all 0.305 grams, I would need at least 38.5 milliliters of my 0.44. How much do I have? 200. I have a lot left over. I will completely react all my aluminum and only need about 39 milliliters. So I've got too much. This is what we would say is an excess. We have a lot. That's my limiting reactant. Okay. Now please remember, you only need to do one of these. However, both of these tell the same tale. All right. These both say the same thing. They're not giving the same numbers, but they give the same story. So again, if I were to use, in this first one, if I used all 200 milliliters of my 0.44, I would need at least 1.58. I only have 0.3. If I used all my aluminum, I would need at least 38.5. I have more than I need. Okay? Yes, Stephanie?
Okay, so what if, like the first one that we did, that we got the 1.58?
Uh-huh.
What if it were to be less than 0.305? Then what happens?
Okay. Let's, again, in our fantasy world here, let's say that it was not 1.58, but maybe like 0.0158. Okay. And again, we're in our fantasy world here. So this was our actual value. So this is how it would read. If I wanted to use all 200 milliliters of my 0.44, I would only need, or I'd need at least this. I have much more. Then that would be the limiting reactant.
Gotcha.
Okay, not done yet. I'm just showing you the options for your limiting reactant step. So now that we know who our limiting reactant is, did you get
Yeah,
38
we're out of
points?
room now.
Okay. All right, now that we, well, I only wanted you to write
Yeah.
the first one.
Oh, you're kidding.
Okay. Now that we know who the limiting reactant is, we don't care about that amount. We do not care about this amount here because it's an excess. The only amount we care about to answer the question is this amount here. But we didn't know which one we were going to be using until we did the limiting reactant step.
What's the other option?
The other option? There is no
Why'd you
option.
change the answer?
Changed what? Oh, yeah. So what was it? 1.58?
Yeah.
Okay. Okay. Now we will not be using that number there. This number here was to tell us which of these is going to run out first. Okay. Now that we know who is the limiting reactant, or the one that's going to run out first, this is the amount that we're going to use to answer the question. And what's the question asking?
Don't know.
Right there.
How much?
How many milligrams of zinc is created?
Wait, yeah, calculate.
Okay. So we start with what we know. So our 0.035 grams of aluminum. Okay, and then we're going to convert that to moles, step 2. Okay. So that's step 2. Step 3, let's get rid of the moles of aluminum. And we're going to moles of zinc. What numbers go in front of that? 3 and 2. Okay, so there's our mole ratio. So step 2, right here. Step 3. Step 4, convert to the desired units, which is converting the moles of zinc to grams first. And what's the mole mass for zinc?
65.39.
Yeah. And what unit does it want it in? Milligrams. So grams go down here, milligrams on top. Which one's bigger?
Grams.
Gram. How many milligrams in a gram?
10 to the third.
Or 1,000. And that's our answer. It was at 1,109.
Yeah.
Okay. Okay. All right, so a lot going on there with limiting reactants. Okay. Whew, that is fun. We got another one. So the question says 325 grams of lead metal. Let's write that. 325 grams. Yeah, grams. Is mixed with a 3.45 molar solution of iron, what is it, 3 nitrate?
Yeah.
So we need 3 of those. Oops, 3 of those. And it says we have 3.45 molar. Calculate the volume. Okay, so we're looking for the volume in milliliters of the iron 3 nitrate needed to completely react with all the lead in the single replacement. Which charge do you want to go with? 2 or 4?
2.
2's a good one.
What?
Okay,
So
for the
you
lead.
You can pick.
You can pick, and normally on something like this, since it has more than one, I will tell you what the charge should be. Okay. Lead is pretty common for being a +2. We rarely use the +4 one. So on this side, we'll have lead nitrate with a +2 charge over here, and then we'll have iron all by itself. Okay. Step 1, write a balanced equation. So we've got 2 there, 3 there, 2 there, and 3 there. Is this a limiting reactant step? Or reactant? Is this a limiting reactant problem?
It's not.
It's not? Is that what I'm hearing?
Yes.
It is not. Very good. The reason why it is not is because we do not have complete information about both of the reactants. And it doesn't ask us about any of these, does it? So it's not a limiting reactant problem. It's asking for the volume needed to completely react with all this. So it's not. It is not a limiting reactant problem. Okay.
Do we need to show that?
Do I need to show what?
Write that down.
No, but I want you to be able to recognize that it's not. Okay, because we don't have complete information.
So if we would have had like 3.45 molarity
In some volume,
and
then I,
some volume, we have to do that
correct.
when we make it.
Greg, I think all of our homework is remembering.
Yeah, it'll be all right. So, and let me ask you this: can we start with this? Can we start with the iron nitrate?
No.
Absolutely not, because the question wants to know what is the volume, so we have to wait till the last step. So start with what you know. This will get you to moles. This cannot get you in a mole amount. There's no way, okay? Because we don't know how much we have. So you have to start with what will give you moles. So 325 grams of lead. Step 1, write a balanced equation. We did. Step 2, change this into moles of lead, which is 200 and something.
7.2.
There we go. Okay, so that right there, step 2, changes the grams into moles. We want to use the mole ratio, moles of lead, and compare it to moles of iron nitrate. And what numbers go in front of that?
2 and 3.
Good. Now, that's step 3. Step 4, change to the desired units. What are my desired units that I'm calculating for? Volume. So, again, just like in the last example, we have to get rid of the unit moles of iron. What goes on top?
Liter.
Liters. Very good. What number goes with the moles?
1.
3.4.
3.45. Okay, because again, this represents 3.45 moles for every liter. And again, everything that's vertical, in other words, for every 1 mole of lead, it's 207.2 grams. If I had 207.2 grams of lead, I have 1 mole. In this reaction, if I want to react 2 moles of lead, iron 3 nitrate, I'm going to need at least 3 moles of lead. Okay, so these are all equal to each other within the problem. So if I had 1 liter of the iron 3 nitrate, it has 3.45 moles in it. What's the last step?
Getting milliliters.
Very good.
3 times
303? Okay. What was that?
Saying I think I know.
Okay. All right. And since I promised you the 5s, I'll do number 5A for you. Hey. The homework problem says when 7.24 moles of magnesium,
Okay, this is limiting reactant.
7.24 moles of magnesium reacts with 3.86 moles of oxygen gas. 3.86 moles. We're going to produce how much product? Well, that's nice. How much? How much? I will be a lot more specific. So let's go with moles. Unless you guys want to go to grams or milligrams or whatever. Okay. All right, so this is a limiting reactant problem because we have mole amounts. So We don't have to do any conversions there. Is this balanced?
Nope.
No. So we need a 2 there and a 2 there. Okay. Let's do our limiting reactant step. Okay. So, which one do you want to start with? Magnesium or oxygen?
Magnesium.
Okay. Doesn't matter. It really doesn't. So 7.24 moles of magnesium. It's already in moles, thank goodness. Use your mole ratio. Moles of oxygen. And we'll go 1 to 2. So what is 7.24 divided by 2? 3.62? Alright, so based on this and the earlier examples, who is my limiting reactant? Who's, I'm sorry, who?
Magnesium.
I hear oxygen, I hear magnesium.
I don't get magnesium.
Okay, well let's talk ourselves
What's
through
that
it.
sentence we're supposed to say again?
Okay. If I use all 7.24 moles of magnesium, if I use it all, I will need at least 3.62 moles of oxygen. That's to react all this magnesium. Do I have at least this amount of oxygen?
Yes.
I actually have more, don't I?
So that's the excess.
This is the excess, good. So this is excess. This is my limiting reactant. Okay. Now, if you would have done it the other way, again, you wouldn't do it a second way, but if you did, okay, I would never ever ask you to do this if you started with the other one. 1 mole of oxygen. So 3.86, 7.72. But if you started this way, this is how you would have read it. If I use 3.86 or all my moles of oxygen, I would need at least 7.72 moles of magnesium. I don't have it.
That
Okay.
makes it easier.
And again,
You don't have it now.
But you won't be able to look at it and be able to tell that. So, but here, if I use all 7.24, I need at least 3.62. I have more. If I use all 3.86 moles of oxygen, I need at least 7.72. I don't have enough. Okay. So once we have that, then we can answer the question, which is what?
How much product will be produced?
How many moles of magnesium?
That math I can do in my head. Hopefully. Yeah, make sure you have the correct mole ratio. Good stuff. Okay? All right, so for the homework, the 4s. Give you a little bit of time.